algorithms in Python. Yeah. About me, that picture. So about me, I'm Pythonista or Python software developer, an active contributor to CPython, the reference implementation of Python programming language. If I'm not writing code, I'm into community development, where I act as a lead for the Python Kampala community, a community of Python enthusiasts here in Uganda. So if you're really interested in interacting with other like-minded Python developers, you can literally check me up and then add you to the WhatsApp forum, right? Yeah, so today, the agenda I have is literally, first of all, I'm going to engage you in a discussion around generators, and then we shall have a look at asynchronous generators. Then before the quarantines, I will literally look at the event loop and then sub-interpreters. So people who literally attended the keynote speech by Lucas Langer, a CoPython developer, he literally talked about much of the aspects that that I'm also going to share during this talk. And I believe that by the end of this discussion, most of us are really going to, get that awareness on different strategies, how we can really write efficient, very performant software programs, right, using the Python programming language. So core concepts to remember: one, generators. Functions that yield values one at a time, allowing efficient iteration over large data sets without consuming excessive memory. Yeah. So the whole point about this is memory management. Yeah. And then coroutines, the building blocks of asynchronous code, allowing you to pause and resume functions efficiently. Then we have a look at asynchronous generators. That's combining the power of generators and coroutines to yield values asynchronously. Don't worry, these are technical terms, but as we proceed, I'm literally going to break these into understandable points that we can literally understand. And then the event loop, the central mechanism that orchestrates the execution of tasks, ensuring non-blocking operations. And then lastly, we shall look at sub-interpreters, leveraging parallelism in Python for independent task execution without shared memory, enabling true parallelism within a single process. All right. Okay. So previously, I'll relate to the keynote speech by Lucas Lang. People who are very attentive, you'll find that this talk is literally maybe an extension to some of the greater, concepts that were discussed by Lucas Langer, right? So we shall start with the generators. Python generators are functions that return a yield statement and can be called continually to generate further values. So the key feature here are: one, generators they use a yield statement instead of return. Normally, when you're writing probably Python programs, there's a return statement that we use to return any value that you want to get. But then when it comes to generators, we use the yield statement. Then there's that aspect of lazy evaluation. So generator produce values lazily, one at a time. So to really understand the concept of generators, it's expedient for us to first understand how memory management is, handled by looking at one of the most used data structures in Python, and that's lists. Yeah. Anyone who has written a Python list before, or has used lists before? Yeah. So we see that when you create a list, usually all elements of values are stored at once in memory, right? This is very fine for large data sets, but it becomes inefficient when you are dealing with large chunks of data or data that is large amounts, yeah? So in that case, it becomes a problem to memory, right? So let's take an example. If you wanted to store maybe 1 million numbers in a list, so Python will literally store all the 1 million numbers in memory simultaneously, and this literally consumes a significant amount of resources. Basically, my focus will be on memory usage, right? So to kind of, come up with a solution that is efficient enough to overcome that problem, we can use generators. So instead of storing all elements in memory at once, what generators do, they generate each value on the fly and yield each value at a time. So this means that instead of loading the entire data set into memory, what a generator does, it generates and computes, and provides one value at a time, yeah? And this actually makes them more memory efficient compared to lists. So we have a generator function flow. With that, before getting to that, I think we can, to make the concept more relatable, we can look at, we can imagine maybe a conveyor belt in a factory. So when you look at the way a conveyor belt functions, is that it does not literally display all products. For example, products in this context, we could literally mean our data, right? So it does not literally display all the products to the worker at once, but what happens is the conveyor belt displays one product to the worker at a time, yeah? So that's the concept that is literally applied to generators. Instead of literally, loading the entire data set into memory at once, it only generates one value at a time and only when it's needed, yeah? So this makes them more memory efficient, especially when dealing with large data sets compared to, data structures like lists, right? So the other concept that comes into play is lazy evaluation. What does it mean? So it means that the generator does not literally do any work until it absolutely has to, yeah? So what this means is when probably instead of, like I said, instead of loading the entire data set into memory at once, it will only generate the next value using the next function. So generators have what we call next function, or even a loop. So what happens is that a generator produces the next value using the next function only when it's needed, yeah? So if it's not, if currently you do not need a value to be yielded back, it will not happen. So in this case, this aspect really makes generators more efficient when dealing with large data sets. Yeah. So we have a generator function flow. We kind of start with there's a start. I'll provide some code snippet to illustrate this. There's a start, an execution loop, then we yield, then we resume, and then loop. Yeah, so we're gonna have to look at this just shortly. So, yeah, we have that. So we have a simple function. It's a count up to, takes in an argument max, and then we have a local variable 1. So while we have a while loop count, if is less or equal to the passed in argument, we yield the count, and then we increment the value by 1. And then, so we have the usage, we have a for loop. Like I said, we generate the next value only when it's needed using the next function, or probably in a loop, right? So this is the for loop that we are literally using. So we are looping through. Sorry. Yep. Can you guys hear me? Much better. So we are literally so the usage of this function is we pass in a number, that's 5, that's literally incremented by 1. So, and then we return that, yeah? So my concept, my idea is not to literally focus on the implementation, but to literally understand how generators work, because there is literally so much documentation on this, and yeah, we can literally go back and research and learn how this is, works. So with that, I would love to talk about asynchronous generators. Yeah, so similarly, asynchronous generators do not deviate from regular generators, right? So to just recap back a bit about regular generators, we said that they generate one value at a time and only when it's needed, yeah? So with this, we see that it makes them more memory efficient compared to this, because a generator, this aspect makes a generator to yield control back to the calling code. Yeah, so the calling code is, it could be that, for example, if you write probably a function and then you use the yield statement, and then probably, for example, this. Yeah, this is the calling code. Yeah, so which means that after an increment we are yielding, we are putting off a value, right? So with that, that attribute makes it possible for generators to iterate efficiently over large data sets, yeah, and this helps in using less memory compared to lists in the other aspect, right? So when it comes to the aspect of asynchronous operations, so in situations where we literally need to deal with tasks that need waiting, probably we could literally talk about making a web request or reading from a file, yeah? We see that we do not literally want to wait our programs. We do not literally want to see our programs idle, yeah, without doing anything, yeah? So to overcome that, we can use the concept of asynchronous programming, and literally I will target this to async generators, yeah? So instead of probably making the whole program to wait, we can use asynchronous generators to perform other tasks, as probably we are waiting for response for this task that is running, yeah? An example could be if probably you are, if probably we are maybe making a request to an external API to fetch data, yeah, like large chunk of data. So instead of just waiting for the entire data set to be fetched and then loaded, we can literally use, between that waiting period, we can literally perform other tasks instead of like having that lag for the whole program to, to just be idle. So in this case, if we take that part of waiting, it will literally cause, the whole program to be not responsive. You have ever seen, probably, you have ever seen programs that are, that's stuck and then stuff freezes. So to literally overcome all such, we can actually use the concept of asynchronous generators. So such asynchronous generators are similar to generators, but can await asynchronous operations inside the generator. So key features defined using the sync def keyword, yeah, and then we use the yield in combination with the wait, yeah. So so in this case, to deeply talk about asynchronous generators. So asynchronous generators, like I said, they are similar to regular generators. However, the key difference between asynchronous generators is asynchronous generators perform asynchronous operations between yielding values. Am I getting people lost? All right. So, so this means that the async generator not only yields control back to the calling code, but also it yields control to any other task that is concurrently running in the same program. So let's take an example. If we have probably maybe chefs in a busy kitchen, probably each having maybe a task to prepare maybe a certain dish, right? And then probably, so in a synchronous kitchen, this will be the aspect. For example, if a chef has to maybe to maybe prepare maybe a certain dish that involves maybe first waiting for water to boil, yeah, they will literally not do anything until that water boils, and then they get to the next task. So, but in an asynchronous kitchen, instead of waiting until the water boils, probably the chef can switch to another task like maybe washing utensils or helping out another chef to do some other task. Yeah, so that's the analogy that we should carry, and that's how asynchronous generators work. In that, in the waiting period, you can literally switch to another task, and if this task that has been that has been running, if it gets to its completion, you can switch back and then like resume from where you stopped. That's how asynchronous generators work. So the whole idea is, I literally want us to really understand these concepts and how we can leverage their strength to rewrite performant software. Yeah. So yeah. Then the other aspect is so this is kind of the sync generator function flow. We have At the start, you yield values asynchronously. So pause at a wait, and then resume and yield. Yeah? So with that, let me see where I think I have some code. No. Okay, sync. Yeah. So just a brief piece of code snippet. We have an async count up to function. It's an asynchronous generator. This function is called, the function name is async count up to, but then the function is an asynchronous generator. So it takes in an argument max, and then we await. So probably during this time of sleeping between 1 second, yeah, we await. This is the waiting period, yeah. So and then we yield the count and then increment it by 1. So we also have another function main, which is an asynchronous function, asynchronous generator, sorry, yeah. So we have an asynchronous loop inside that prints, the number of the passed-in number, the argument that's passed into the async count up to function. Yeah. So literally, this is how one will literally implement an asynchronous generator. So we said that the key feature is to take point of async def. That's a keyword. We utilize the presence of the await and then yield to achieve the functionality of asynchronous generators. Yeah, then we will literally look at the event loop. So the event loop is an important aspect when it comes to asynchronous programming because it acts as an orchestration to manage all tasks. In this case, I will refer to them as quarantines. Yeah. So the event loop, the main function of the event loop is it manages the scheduling, resuming, and then pausing of quarantines or tasks that are running. Yeah. So to first understand, what is a quarantine? Quarantines are similar to advanced functions. And what is an advanced function? An advanced function, in this case in programming, is a complex or specialized function that goes beyond the basic concept of input, output. Yeah. So what I mean is it's a function that provides additional power or flexibility to an engineer to write more expressive, modular, and clean code. And an example could be a higher order function, a disclosure, or I mean a closure, not disclosure, sorry, or a decorator. Yeah, that could be. Those could be some of examples of advanced functions I can mention. Yeah. So in this case, when you look at the event loop, so the event loop looks through when you're writing quarantines or when you're dealing with the concept of quarantines, what an event loop does, it tracks all the present quarantines at the moment in the program, and then it schedules what should run, what should resume, and what should pause. Yeah. Take an example if take an example if we literally had, let's look at an example of a project manager, right? Maybe managing a team of 3 engineers, 1 back engineer, an integration engineer, and then you have a front engineer, right? So for an integration engineer to probably do their work, probably integrating some of software components that are done both on the back end and the front end, they will have to wait for these back end and front end guys to complete their task, right? So in that case, you see that the question will be, what will this integration engineer do if these guys are not done with their work? They will just sit idle, right? Here. But then a good project manager doesn't really let the integration engineer just sit idle. So instead, to keep that person maybe productive, he'll let them do some other work as probably these guys are finishing up. And when they finish up, he'll switch up and then, gets to his work. Yeah. So that's the point an event loop, does, is that in this aspect, for example, if there is, if for example, we are dealing with a task that needs to maybe to await something. For example, if we're waiting for user input to make any further probably, no, for example, if probably we are to, let me use the previous example that I used. If we are to probably use, if we are probably use an example where we have to fetch data from an external API, right, by triggering probably an endpoint. So we know that probably if this data is large, it's going to take some time to be fetched, right? But then the thing is, we literally have other programs probably that are running within we have other tasks that are running within the program. So what this does is, as we are literally, as we are literally waiting for this, data to be fetched, yeah, the event loop can pause, yeah, and then probably checks for other, tasks that can be, triggered to run, yeah. So if the completion, if the completion of the previously triggered task is achieved, yeah, then the other task also resumes running, yeah. So that happens in a loop that, okay, it checks, I have maybe a task A, quarantine A and B and C. So it checks, okay, if quarantine A maybe faces an obstacle that hinders its execution. Oh. All right, thank you. So when it finds out that, so it schedules which tasks to run, resume, and then pause. Yeah. So lastly, I talked about quarantines, and then I'll talk about lastly sub-interpreters. Yeah. We are talked about the sub-interpreter. So I'll begin with the concept of the GIL. The GIL is a well-known limitation of the Python's probably threading model. So the GIL, or the global interpreter lock, is a mechanism that is used by the Python interpreter to only ensure that only one Python thread executes the Python bytecode. The bytecode is the code that you write, or the code that you want to run, right? So, so with this is this affects like true parallelism, yeah. But then the way how to overcome that is the use of sub-interpreters. So sub-interpreters allow multiple isolated Python interpreters to run within the same process, but under isolated environments. Yeah, so which means that they literally are like how operating system processes work. Yeah, operating system processes work, where they have, probably they have the same memory space and then probably execute independently. But then sub-interpreters, what they do, they provide a lightweight alternative to processes by running within the same processes, but under different isolated environments. Yeah. For more references, look at Python enhancement proposal by Eric Snow. That's 734554 to get more, ideas about how sub-interpreters work, and then all the other concepts. Thank you so much.
Thank you very much, our dear speaker.